Hello. So, in this video, we're going to be tackling sort of almost the opposite direction of what we normally do. So, thus far, we've been covering all kinds of ways of interpreting different levels and types of derivatives sort of graphically. So we usually try to use some sort of visual representation like a graph to sort of motivate, right, some information about the derivative and sort of pull something out of it. In this case, we're actually going to be going the other direction. So what we want to do is use information about derivatives to try to create a sort of nice version of a graph. That's our sort of overall goal. So in particular, we're going to be using derivatives to create this sort of detailed sketch version of a function that sort of otherwise you'd have no real hope of being able to do. So, you know, if we sort of think back to in precalculus and we were like, okay, you know, you could graph x squared or maybe some sort of linear movement, right? Some translation or transformation of a function. We could do that kind of thing, but sort of much more complicated stuff, maybe not. So that's what we're going to be trying to do. There's a couple things to keep in mind for this video though. So the first thing is that this is really one of those things that's sort of best learned by doing a bunch of examples. So we're going to have a bunch of example videos for exactly this reason where, you know, we'll go through actual concrete things and do, you know, actual computations and get through all the little details and do everything all the way out. So again, that is sort of a very helpful way of seeing how this is done, and you definitely want to watch those. But it's sort of easy to get lost in all of those sort of gritty details and all those careful computations to get all the information that we're going to need and sort of miss what's happening in the bigger picture. So as a result, be aware that like in this video that we're doing right now, we're going to sort of be deliberately glossing over, omitting a lot of these very careful sort of line-by-line calculations, because in this video specifically, we're after that sort of big picture, like how do we actually use the information we're given? So in particular, the example videos are going to show how to do all the calculations and which calculations need to be done and sort of how to go through all of this stuff. This video is more about interpreting the result of those calculations, right? So what are the calculations telling us and how do we translate that information into an actual picture? So for that reason, don't feel alarmed if you're not sure exactly how a calculation happened or what was done or sort of where a specific equation came from. That's all stuff that's going to be sort of done in detail in the example videos. Here, you want to focus on how we translate the result of a calculation, right? The end sort of summary bit into a graph, okay? And you'll see what I mean by that as we go forward. So we're going to do an example, but again, we're going to be doing an example where sort of all of the calculations have been done in the background for us. I'm not going to go through exactly how to get each step. I'm just going to be like, here's the result of that calculation. And if you're like, how on earth did you do that? Don't worry about that part. That's what the example videos are for. Just sort of take it on faith. The idea here is that we want to see what we then do with that information. Okay, so all that being said, let's look at this function. So we have this function, f of x is x cubed minus x squared minus x plus 1. And our goal is to graph sort of a detailed version of this thing. So right off the bat, it's sort of not clear how this thing would be sort of graphed using just precalculus, right? Like you might have an idea it's a cubic, so you have roughly the shape, but as to exactly where it is and sort of where the important parts are, that's not as clear. So what do we do? So first step, we factor it out. We want to know where the x-intercepts are, so we're going to factor the initial thing. But this is a calculus class, so unsurprisingly, the next couple steps, we're going to calculate and then factor out our derivatives. So we take the first derivative, we factor it, take the second derivative. I don't really need to factor because it's sort of close enough. I could pull out a 2, but I'm not going to worry about that. The reason I wanted to factor was because I want to find the zeros. So I'm going to record those zeros, right? So I have f of x has the zeros at -1 and 1, right? Pulling it out of these pieces here. F prime of x has 1 at -1/3 from that part and 1 from the second part. And f double prime of x has 1 at 1/3, right? I can set that equal to 0 and solve. So I'm going to list all the zeros. I got those for the f, f prime, and f double prime. Then my next step, I'm going to build a sign chart. So the idea of the sign chart, right, is I record all of these zeros for each of my piece, right, each of my f and then f prime and then f double prime. So that's what these things are down at the bottom. And then I test that original sort of factored form for each of them and jot down whether it's sort of negative or positive in each of the little sections that I'm looking at. Now, I want to do that because I want to use this sign chart to find the maximums, minimums, and or any inflection points for each of those x values, right? I want to know is -1, a min, max, neither, inflection point, whatever. So for example, at -1/3, right, when x is -1/3, that f prime is going from positive to negative, right? So it's going up and then down. So that's telling me that that's going to be a maximum. Likewise, the value for x equals 1, right, over here, this is going, the derivative is going down and then up, right? So it's down and then up. So that's telling you that that's going to be a minimum, right? Likewise, at x is 1/3, my second derivative is changing sign. So that tells me that when x is 1/3, I'm getting an inflection point, right? So this is telling me sort of the x values of all of these things. But I actually want the actual points that I'm going to put on the graph. So I have those three, plus I want to know what the y-intercept is, which occurs when x equals 0. So remember, right, I had my -1 and 1 were x-intercepts from my original function, right? Those were when I factored it. Then I have the 0, 1, that's plugging in the 0 and finding the y-intercept. And then I have these local minimum and maximum and inflection point, which again I get by just plugging in the relevant x value and calculating out the actual function value at that point. Okay, so I'd plug in, say, -1/3, and that would get me 32/27 as the y value if I plugged it in here. Again, the specifics of the actual calculations and the important part. The important part here is that we sort of found which x values were important, right? The 1, -1, -1/3, +1/3. Then we want 0 to get the y-intercept, and we plugged in all of those things and got all of these points, okay? So I have all of these, which are points on the graph, and I'm going to take those points and I'm going to graph those points specifically, sort of as my first step. So if I look at a nice xy axis, I'm going to put those points on there, right? So this is the -1, 0, and the 1, 0, and the 0, 1. I had -1/3 and 32/27 or whatever, right? That would be this point up here. So that's what I'm doing. I have all of those points written down. Now, it can be helpful, and I very much encourage that you sort of jot down a light sort of sketch that represents what these points represented. So for example, this point at x equals -1/3, we knew that that was a maximum, and we know that the 1, 0 was a minimum. So we can put these sort of light little parabola sketch pieces through it to tell me that that's what's happening, right? So here I know it's a maximum, so it goes up to the point and then down. And over here, we knew this was a minimum, so it goes down and then up, right? I'm not claiming that this sort of is the exact path that the thing is going to go through, that the curve is going to take. It's just that that's the type of path, so that when I sketch it sort of at the end, I know what it's supposed to look like as it goes through that point. And then I'm going to do that for these other points as well. So the 0, 1, right, this point here, the only sort of part that was important about that was that it was the intercept, right? So it's not doing anything weird through that. But here at this 1/3, right, the x equals 1/3, this was some sort of inflection point where it was going from negative, so it was going concave down to concave up, right? So it's going to look like this sort of weird over and then down and then over kind of weird thing. And on this left part, we knew that the function went from negative to positive as it passed through that. So again, I'm just going to put in sort of weird little light sketches that show me this is the kind of behavior that's going through this point. Once I have that done for all the points that I have sort of listed where it makes sense, again, the y-intercept is an important point, but it doesn't sort of represent any curve nature. It was just where it goes through that point. Once I've done this, then I can sort of try to trace through, right? So I look at, for example, if I want to go left to right, I'm like, okay, I have to start down here somewhere. I have to come up and through this point. Then when I go through this point, I know that I have to go up and then down. Then I have to go through the next point, then this next point. But when I go through this one, it should sort of curve over and down and up-ish, whatever we mean by that. And then as it goes through this other point, I know that it goes down and then sort of bounces off the x-axis and goes up, right? So this is why I have it written sort of lightly sketched in there so that when I try to sketch the actual graph, I get something like this, right? Where again, notice that it doesn't really, like the parabola doesn't line up perfectly, and that's totally fine. It was just there to tell me the kind of shape that goes through rather than representing the actual curve itself, okay? So this would then be my detailed sketch, right? It has where the maximums are and the minimums are. It has the intercepts. It has points of inflection. So it has all of the sort of pieces that we know how to find in calculus. Okay. So what do we do? So we can use the ideas from derivatives like the concavity, local extrema, as well as some concrete values like the intercepts. And we can make a much more detailed sketch of a curve, of a graph, than we sort of knew how to do before in a pre-calculus setting. So now that we have all this calculus at our disposal, we can make much better versions of these graphs. And being able to do that, so being able to have sort of a reasonably accurate graph, this can be a very powerful tool, right? When you're trying to figure out, like if you're trying to present data and you want to show trends, or even trying to decide sort of what a good sort of course of action might be for like your company or whatever, it's useful to have sort of really representative sort of graphical information so you can see sort of in better comparison, right? You can look at two different sort of projections and see the more detailed they are, the sort of more accurate and better of a comparison you can make, okay? So that is that.